Good morning, George Romanic here. We are going to continue to explore Coriolis Force. Today's video is very specific and you will see a big revelation towards the end of this video. The problem is now on your screens. So as you can see, we are given wind vector. Mass of the parcel of air is 1 kilogram and we have two latitudes, one in the Northern Hemisphere, another one in the Southern Hemisphere, and we need to find the Coriolis Force, a vector of the Coriolis Force. By now you should know that this wind velocity means, if these numbers are in meters per second, that this is 3 meters per second towards the east, 7 meters per second towards the south. South is negative, remember. North would be positive, and 5 meters per second in the vertical direction, namely upwards. So we know that Coriolis force is given by this vector equation, negative 2m omega cross v, where m is the mass of the air, and we already see from the setup of the problem that this is just 1. Omega is angular velocity of the Earth, approximately 7.3 times 10 to power negative 5 radians per second in terms of magnitude, and v is given over here. So we will solve this cross product using determinants, which means that F Coriolis is equal negative 2 determinant. First row are unit vectors I, j, k. Second row is the first vector in the cross product, omega, and by now I demonstrated at least 4 or 5 times how to derive components of the omega, so I'm not going to do it again. I will just tell you that components of the omega are 0 in the zonal direction. In the meridional direction, omega cosine phi, where this omega without vector is the intensity of angular velocity, phi is latitude, and in the vertical direction, omega sine phi. And the third row is the second vector in the cross product, and we see components here 3, negative 7, and 5. So this is further equal. I will write it here on the top of the blackboard so I save a little bit of space. Well, we need to solve this determinant. And that would be negative 2 that will multiply in the I direction, so I cross this column, this row, I will have 5 omega cosine phi minus, but because of this minus, it will be plus. So plus 7 omega sine phi minus in the j direction. In the j direction, I cross this row and this column. I will get 0 minus 3 omega sine phi. 0 minus 3 omega sine phi. And plus, in the k direction, I cross this row, I cross this column, I will get 0 minus 3 omega cosine phi. And now we just need to multiply all these terms with this negative 2. So 2 times 5 will be negative 10 omega cosine phi minus 2 times 7 is 14 omega sine phi, and that will be in the I direction. Now in the J direction, this minus and this minus will give me plus, but because of this minus over here, I will again get negative, so it will be negative 3 times 2 is 6 omega sine phi, and this minus will, and that's in the J direction, so this minus and this minus will give me plus. 3 times 2 is 6 omega cosine phi in the K direction. Okay. So now we basically can plug in the values and calculate each component of the Coriolis force, because we know phi is latitude. They are given two different latitudes, and we know omega, as I said many times, omega is approximately 2 pi over 1 day. Now you put day in seconds and you calculate. It's approximately because 1 day is not exactly 24 hours, so the value that I am using is not exactly correct. I say omega is 7.272 times 10 to negative power 5 radians per second. The real value to some decimal place disagrees because, as I said, 1 day is not exactly 24 hours, but for this purpose, these small differences are not so important. So we can plug in the numbers and calculate this. And of course, I don't have it in my head. So in the A case, and A is 37 degrees north, we have the result that says that F Coriolis is equal negative 0.0012 in the I direction minus 2.63 times, this is times, not x, 10 to power negative 4 in the J direction, and plus 3.48 times 10 to power negative 4 in the K direction. And in the B case, and B case is 37 degrees south, so now you have to know that the Southern Hemisphere gives negative latitudes, so this phi will be a negative angle for the Southern Hemispheres. I discussed this in one or several of my previous videos. So with that in mind, Coriolis force for the B is equal 3.19 times 10 to power negative 5 in the I direction plus 2.63 times 10 to power negative 4 in the J direction, and plus 3.48 times 10 to power negative 4 in the K direction. So I told you that at the end of this video there will be a relatively large revelation and something that might shock you. And that is the following. Let's compare these two expressions. This number and this number are the same to a sign. This one is positive, this one is negative. These two numbers are identically same, even to a sign. But these two numbers, which are the most important here, are actually different. Which means that in the meridional direction, Coriolis force for the Northern Hemisphere and Southern Hemisphere is the same up to a sign. In the vertical direction, it is exactly the same, but in the zonal direction, namely west to east, positive eastward, this force is actually different for the Northern and Southern Hemisphere. Now, why is that the case? This is what we will now discuss. And there are two ways to discuss this. Way number one is to address this mathematically, and option number two, to talk about this in the physical sense. First, we do it mathematically. Mathematically, you have to know that cosine of a negative angle is cosine of that angle. Namely, cosine doesn't care about the sign of an angle. However, trigonometric function sine of a negative angle is negative sine of that angle. Now, knowing this, if we go to this equation now, notice that this term has sine. So, for positive angle, namely Northern Hemisphere, this will be negative. For negative angle, namely Southern Hemisphere, this will be positive number because this will give us negative sign and this negative will give us positive. So you see that Coriolis force in the meridional direction has opposite action. Let's look at here. Here is the vertical component of the Coriolis force. We have cosine of phi, and look, cosine doesn't care about the sign of an angle. So this will be positive 6 omega cosine phi regardless of the phi, and indeed we have positive numbers over here. Now we can also look these two additionally and say this is negative in the j direction and this is in the Northern Hemisphere, so positive j is northward, which means deviation will be towards the south. Okay? Here deviation will be towards the north in the Southern Hemisphere. Here in the vertical direction, the force will always act upwards because these are positive numbers and positive k is up. Which means if the air is rising, if the air is moving towards the east, Coriolis force will always try to push it up regardless of the hemisphere. Now, let's look into this first term associated with the I unit vector. We see that this term has two components. And the fact it has two components results in this term not being, so to speak, symmetric between Northern and Southern Hemisphere the way these terms are up to a sign or not even to a sign in the case of the k direction. Here, notice, we have negative 10 omega cosine phi. When I use Northern Hemisphere, this will be negative. When I use Southern Hemisphere, this will again be negative because cosine doesn't care about the sign of an angle. So this is a negative number in this case, whatever happens. However, this component over here of the expression will change sign among two hemispheres. This will be negative in the case of the Northern Hemisphere, where phi is positive, and when phi is negative, this will reverse the sign and this will be positive. And now when you are adding or subtracting these two terms, because this one is unchanged in respect to sign and this one changes sign, when you add them together, you get different component of the Coriolis force in the zonal direction in the Northern Hemisphere and the Southern Hemisphere. So this would be mathematical explanation where we are just tracking sines and cosines, and we are aware of this mathematical identity, trigonometric identity, related to cosines and sines in terms of the sine of the angle. Now, what would be the physical explanation? This is more interesting. Well, the physical explanation, I need to erase something, and I don't see an eraser. Think about this. There is no, I don't have anything to erase blackboard. I have to go to my office to find something to erase blackboard. Don't go anywhere, I'll be back in a few minutes. Are you still here? Good. I found it in another classroom. So, what I said is we would like to analyze this physically. To do that, let's first determine horizontal direction of this velocity vector. So if we take a right-handed Cartesian coordinate system, and here is positive u towards the east, and here is positive v towards the north, notice we have 3 units in the I direction, so 1, 2, 3, and negative 7 units in the J direction, so 1, 2, 3, 4, 5, 6, 7. So approximately this would be horizontal wind velocity for this vector, and we see that in the vertical direction, which is W, the wind is positive. That means coming out of the blackboard, raising air. Air is getting up. So now, when we determine this, let's look at the following. Let's say this is 0 degrees or equator in terms of latitudes. So 37 degrees north, let's say, is here, 37 degrees north, and then here somewhere would be 37 degrees south. So if we take a parcel of air of unit mass over here, we see that in horizontal direction, wind vector will be something like this. And over here, it's the same. It would be something like this. Well, I didn't copy it exactly, very exactly, but you get the point. Now, let's analyze what we have here. Let's first look J direction of the vector. We see here in the Northern Hemisphere, deviation will be towards the right. And towards the right means like this, in respect to the original motion. In the Southern Hemisphere, I demonstrated that in previous videos, deviation will be towards the left, like so. Now, because here deviation is towards the south, and that is to the right of this original vector, towards the south is negative meridional direction, and indeed we have negative meridional direction. For the Southern Hemisphere, deviation is towards the left, and in this case, left is veering towards the north, and north is positive, and that's why you have plus over here. Now, also notice that the wind in the zonal direction in both cases is towards the east. So here would be west, of course, here would be east, here would be north, and here would be south. So you can see that in both cases, original wind vector is directed towards the east, namely 3 units towards the east, and in that case, in both hemispheres, Coriolis force deflects motion up. Now let's look at this term over here. This term is completely different among 2 hemispheres. But to understand that, we have to look into these 2 terms separately. First of all, we have to remember that we have upward motion in both cases, and quite strong, 5 meters per second up. Now, this tells us, this over here, that regardless of the hemisphere, when we have motion up, getting out of the page like this, that will be deviated towards the west. So this wind vector will be deviated towards the west in terms of this term over here, because this term as well as this term do not depend on latitude. Terms associated with cosine, do not depend on the hemisphere, not latitude. They depend on latitude. Terms associated with cosine phi do not depend on the hemisphere. So air that is ascending will move towards the west regardless of the hemisphere. However, this component over here does depend on the hemisphere, and we see this will be negative in the Northern Hemisphere and it will be positive in the Southern Hemisphere. Let's see why. Well, in the Northern Hemisphere, this is deviating towards the right. But in respect to this motion, towards the right would be towards the west. And that makes sense to have negative sign, because west is negative direction and east is positive direction in the zonal direction. However, here for the Southern Hemisphere, this original vector is deviating towards the left. And left is towards the east, and east, as I just said, is positive, and that's why this term will be positive over the Southern Hemisphere. And now you understand that if we look into these 2 terms, for the Southern Hemisphere, this sine turn moves the parcel of air towards the east, but the cosine term moves it towards the west. They battle each other, and at the end of the day, their addition is a very small number order of magnitude 10 to power negative 5 newtons. But in the Northern Hemisphere, both of these are negative, so the sine term moves this towards the west, and the cosine term also moves this towards the west, so they are just satisfied with each other, and they combine nicely to produce negative force towards the west, and that force is much stronger than in the southern direction, because these two act together in the Northern Hemisphere rather than battling each other as they do in the Southern Hemisphere. So I hope this, together with the mathematical properties of the cosine and sine, help you to understand this very nice relation between the Coriolis force in the Northern and Southern Hemisphere. Now, another thing that I would like to mention here is that in atmospheric sciences, more often than not, we neglect this term, and we also neglect this term. The reason, I talked about that in my video on traditional approximation, the reason is the following. Vertical motions in the atmosphere, especially at large scales, synoptic scales and beyond, planetary scales, are very, very weak. So vertical motions result in a Coriolis force that is very, very weak compared to the horizontal components of the Coriolis force, and these are two horizontal components that are very important. Now, this horizontal, so this component disappears. This component also disappears because motions in a troposphere, first 10 kilometers, are predominantly horizontal. So you don't get very big, as I just said, deviations in the vertical direction at very large scales. So this term and this term tend to be neglected. So if we would look at this vector and to make it more realistic for atmospheric sciences, this would probably be, let's say, 3, -7, 0.05, not 5 meters per second at synoptic scales. Order of centimeters per second rather than meters per second. So this is way exaggerated compared to what we usually observe in the atmosphere at synoptic scales. However, you might say, what about other scales? What about mesoscales? What about local scales, wind around buildings and so on? Well, in that case, you can have extremely high vertical velocities, even larger than horizontal velocities, 10, 20, 30, 50 meters per second vertical velocities, but they last for very short time. And we know that Coriolis force depends on the duration of the motion, and in fact, it non-linearly depends to the power of 2. And because these strong vertical motions last for a very short period of time, we once again can neglect that component of the Coriolis force. If you are interested in the vertical component of the Coriolis force, I already discussed that in one of the previous videos, then close to the equator, vertical component of the Coriolis force is much, much stronger than at higher latitudes, and namely it completely disappears in northern and southern poles. And of course, by now you should know that quite opposite holds for the horizontal component of the Coriolis force. It is the strongest at the north and south pole, and it completely disappears above the equator. And you can see that also from these expressions, because cosine of phi is 1 at the equator, because phi is 0, cosine of 0 is 1, but sine of 0 is 0, which means horizontal components disappear in the, terms associated with sine disappear near the equator, and they are maximized at the northern and southern pole. So, this is getting long video. I will stop here. I hope you understand the difference between the Coriolis force for the northern and southern hemisphere, looking in this particular example And now you know how to interpret that mathematically and physically. In the next video, we will generalize this. It will be a very short video, I think. We will generalize this for any three components and not just specific 3, -7, 5. But before generalizing it, I thought it is useful to give a particular example so you can see with real numbers how the things look like. Until next video, goodbye.